Welcome to an introduction to chemistry brought to you by Parkbench Tutors. For more information about Parkbench Tutors, look us up on Facebook or visit parkbenchtutors.com. In this short podcast, which is a support tutorial, we're going to look at the concept of the mole in chemistry. The mole is a quantity of particles, and it doesn't matter what the particles are. In chemistry, they can be atoms, they can be molecules, they can be ions, or they can be electrons. And the number of particles in a mole is 6.02 times 10 to the power of 23, which is referred to as Avogadro's number. And he derived that number by determining that equal volumes of different gases at the same temperature and pressure had equal number of molecules. Now, what do we mean by the same temperature and pressure? Well, first of all, for those who like calculations, if you want a true figure for Avogadro's number, it's close to 6.02221415 times 10 to the power of 23, but we're just going to use 6.02 for the purpose of this podcast. Okay, let's go back to this idea of temperature and pressure. We measure at standard temperature and standard pressure, and standard temperature is 273.15 degrees Kelvin, and standard pressure is 101.3 kilopascals, or 1 atmosphere. There are other ways of expressing standard temperature and pressure, but if you want them in SI units, it should be in Kelvin and in pascals. So the standard volume of 1 mole of an ideal gas at standard temperature and pressure is 22.4 litres. So it means if you have things at the same temperature and pressure, it doesn't matter whether you have a litre of hydrogen or a litre of oxygen or a litre of carbon dioxide, they're all going to contain the same number of molecules, and that's what we refer to as Avogadro's law. So the mole itself, the mole is just a number. The units depend on what we're going to measure. So we can have a mole of apples, we can have a mole of Ferrari cars, we can have a mole of bananas, but in each case we'd have 6.02 times 10 to the power of 23. Now, what about molar mass? The molar mass of something is the mass obtained by adding the relevant atomic masses, and then we write the answer in grams. So let's take calcium carbonate as an example. The formula is CaCO3, so there's 1 atom of calcium, 1 atom of carbon, and then 3 atoms of oxygen. So if we take the atomic mass of calcium as 40, the atomic mass of carbon is 12, the atomic mass of oxygen is 16, so 3 lots of 16 of 48. Add those up, we'll have 100. So the molar mass for calcium carbonate is 100 grams. That's sometimes known as the gram formula weight. It's also the mass of 1 mole of the material expressed in terms of grams. Let's have another example here, a mole of potassium aluminum sulfate. So we have 1 atom of potassium there. You go ahead, I can see 1 atom of aluminum, and if I look, I've got the sulfate group twice, so 2 lots of sulfur, which is 64, and 4 lots of oxygen twice, that's twice, but it's 8 lots of oxygen there. And then I've got the water, so I've got 12 lots of water to add. That's 24 lots of hydrogen, 12 lots of oxygen. Okay, so if I add up all those masses, I have 474 grams. Okay, so you should be able to work out quite easily now what's the mass of 1 mole of sodium sulfate. You can see how many atoms of sodium you have, how many atoms of sulfur, and how many atoms of oxygen you've got, hopefully. So sodium has atomic mass 22.99, sulfur 32.07, oxygen 16. So if I add those up, 2 lots of sodium 45.98, 1 lot of sulfur 32.07, 4 lots of oxygen, which is 64, I've got a total of 142.05 grams. So that's my molar mass there. Now, obviously we're not always going to work in exact moles, so how many grams would we have in half a mole of something? Let's take half a mole of barium nitrate, formula BaNO3 twice. So barium has atomic mass 137.3, nitrogen 14.01, oxygen 16. Okay, so 1 lot of barium, 137.3. 2 lots of nitrogen, 28.02, and twice 3 is 6 lots of oxygen at 96. Add all of those up, 261.32, so that would be a mole of barium nitrate. So 1 mole is 261.32, then half a mole is going to be half of that, which is 130.66 grams. Okay, what's the mass of 1 mole of hydrogen? So the mass of 1 mole of hydrogen is equal to the atomic mass, which is 1 gram. It's actually slightly more than that. The mass of 1 mole of hydrogen molecules will equal 2 grams. That's because each hydrogen molecule has 2 atoms in it. So 1 mole of hydrogen atoms contains 6.02 times 10 to the 23 atoms. But if we talk about a mole of hydrogen molecules, then it still is a figure of 6.02 times 10 to the 23, right? Each molecule, of course, consists of the 2 hydrogen atoms, but the mole must remain the same number, whether we're talking about atoms, molecules, or ions, or whatever. So a mole of hydrogen gas contains 6.02 times 10 to the 23 molecules, but in that mole of hydrogen molecules there are 2 moles of hydrogen atoms. Now let's look at calculating the mass of a molecule. Let's take oxygen for a start. We know that the mass of a mole of oxygen, it's O2, is 2 times 16, that's 32 grams. We know how many molecules there are in that mole, 6.02 times 10 to the power of 23. So if I divide one by the other, divide my 32 by 6.02 times 10 to the power of 23, that gives me the mass of 1 molecule, which works out as 5.32 times 10 to the minus 23 grams. So if we wanted to do that for hydrogen, we'll use atomic mass 1.008. So the mass of a mole of hydrogen gas, remember hydrogen gas is H2, will come to 2.016 grams. Now, how many molecules are there? There are 6.02 times 10 to the 23 molecules in that mole of hydrogen gas. So if I divide by my 2.016 by 6.02 times 10 to the 23 grams, that gives me the mass of a molecule of hydrogen, which works out as 3.349 times 10 to the minus 24 grams. You can do the same thing with chlorine. If you know the atomic mass of chlorine is 35.45, and chlorine gas at Cl2 contains 2 atoms of chlorine, we know that the mole of chlorine gas is 70.90 grams. We know there are 6.02 times 10 to the power of 23 molecules in that mole of chlorine gas. So divide 70.90 by 6.02 times 10 to the 23 grams, you have the mass of a molecule of chlorine. Right. So, moles and elements, how much of these have we got? The mass of an element is equal to the moles of number of element times the atomic molar mass. So 1 mole we determined for adding up the molar mass, or the atomic masses rather, to get the molar mass. So if the mass of an element is equal to the moles of an element times the atomic molar mass, by rearranging that, the moles of an element are equal to the mass of an element divided by the atomic molar mass. If I consider moles and compounds, the mass of a compound is equal to the moles of a compound multiplied by the molecular molar mass. So if I rearrange that again to get the moles of a compound, I take the mass of the compound and divide by the molecular molar mass. Remember, if we're looking at the molecules of a compound, the number of molecules that we have, right, the number of molecules is equal to the moles of molecules times that figure, Avogadro's number, 6.02 times 10 to the power of 23. Therefore, the moles of molecules will be equal to the number of molecules divided by 6.02 times 10 to the power of 23. Now finally, if we look at the atoms of elements, The number of atoms present will be equal to the number of moles that we have times 6.02 times 10 to the 23. Therefore the number of moles that we have will be equal to the number of atoms divided by 6.02 times 10 to the power of 23. That ends this short podcast on chemistry and an introduction to moles, brought to you by Parkbench Tutors, narrated by David Hopcroft. Thank you for watching and for listening. For more information about Parkbench Tutors, please look us up on Facebook or visit parkbenchtutors.com. We wish you success in your studies, and if you visit parkbenchtutors.com you can have access to further resources.